So how much VGS is greater than VT? How much is VOV? The channel depth is directly proportional to that overdriven voltage, right? So now if the channel is formed, right? I have applied a voltage VGS greater than VT, right? And for VGS greater than VT, how much is greater? We have accounted this parameter as VOV, right? So if I now increase VDS, the voltage from drain to source, right? But keeping this VDS small in millivolts, right? Then we are having a current from drain to source, right? You can see we are having a current from drain to source. The current, the charge carriers, electrons can easily move from drain. Actually, current charge carriers, electron is moving from source to drain. The conventional current direction would be from drain to source. Okay, and now if I increase VDS slowly, obviously in millivolts, but slowly, then by increasing this VDS slowly in millivolts, I can expect more current, right? Almost a straight line relation from VDS in millivolts to ID, right? So now I can write ID is equal to the conductivity, the conductance of the transistor multiplied by the applied voltage VDS, right? And how about GDS? GDS is equal to KNVOV, KNVOV into VDS, okay? Because GDS is KNVOV. And how about this diagram? Here, for this slide only, please understand that the source, you are having a voltage value increasing from bottom to top, okay? And you are having source at the lowest potential as compared to the other terminals, right? And for example, because in this slide you have connected your source to ground, suppose this is the zero potential, right? And it is already mentioned that every device would be having a threshold voltage for which the channel is minimum channel is formed to be used for conduction, right? So this is the minimum value of VT. So obviously, for example, 0.7 value, if this is 0, then this value will be 0.7, okay? For example, VT is 1.2, then this value will be 1.2 because this is 0, okay? And you are already said that you have applied your gate with respect to source greater than VT. It means your gate potential will be greater than this threshold voltage, right? Greater than that. How much greater? Subtract these two things. The distance between these two things will be VOV. So you can see from VT to VG is overdriven voltage. This is the one VOV. Okay, right? Please let this part for the upcoming slide. Okay, so you can see almost a straight line with slope proportional to VOV, right? Channel depth. So now if I increase VGS further, VDS further, then basically your source is grounded, this source is grounded, this gate potential is applied, and this gate potential is uniform on the whole gate terminal, right? So it means the channel was uniform in this case, right? Channel was uniform from source and from drain. The depth is same, but because this drain potential as the drain is increased, right? So it means the difference with the difference of gate to source is still the same. It means the depth here, channel depth, will be the same as per the previous case, but this case, right? Here also same, but because drain potential is increased, it's not zero, right? Or it's not in millivolts, right? So it means that gate to drain difference, potential difference is lowered, right? So it means the depth of channel at the drain side will be reduced, right? So you can see previously it was here, but now it is reduced, right? Why? Because your drain is higher than source. It's not same as source. That's why the difference between the depth of channel will be lowered. How much lower? This is proportional to VOV. This is actually proportional to VOV minus VDS. The as much as your VDS is higher, VOV having a difference, then your channel depth will be reduced, right? So now I can introduce another thing. ID is equal to conductance multiplied by voltage, right? So now conductance was GDS is equal to KNVOV. So I have to put KNVOV into VDS. But since your depth is differing from source to drain, it means your conductance is actually is not only depending on VOV, because conductance is from drain to source, right? And channel depth will affect the conductance, right? Here channel depth is proportional to VOV, right? Channel depth also, right? So what should I take? VOV? No. Basically, voltage is dropping along the channel. This is the reduction of voltages. Okay, so it means I have to take this value. So this value is VOV minus VDS. Here we are again having VOV only. Previously we took only VOV because the channel depth is same, proportional to VOV. But now here VOV minus VDS is the channel depth, which directly affect the conductance, and here it is VOV. So what should I take? So basically we can take the middle of this value, here to here. So the middle of this and this value is VOV minus half VDS. Okay, at the middle of the channel. If channel length is L, then L by 2 is the middle, and middle we are having midpoint formula between this and this. So now I can use, instead of VOV, VOV minus half VDS, because your conductance is actually conductance parameter multiplied by the depth of the channel, which is the potential for which the depth is introduced, right? So depth is actually not linear, it is varying in nature. So we have to put a best relation, right? So now you can see your relation is no more linear, right? It's having a band here, right? So curved bands because the channel resistance increases with VDS, right? Increase channel resistance. If conductance is reducing, it means conductance is reducing, it means resistance is increasing, right? So the same statement. Okay. So now our ID is actually VOKN VOV minus half VDS into VDS, because your conductance is changed from this to this, your new ID will be here. So it means this is this linear relation having this only, but as soon as it bends, this one needs to be used. Okay, please don't get confused. You can use only this formula for the whole region, right? Why? Because you see previously your drain to source voltage was in millivolts. This relation exists for only for millivolts. So even if you use this formula for that region also, then millivolts divided by 2 can be neglected, so this thing intact, right? So it means you can use only this formula for this region. Okay, so if you increase VDS further, your curves bends more, right? And this formula intact, right? But a point occurs when you increase VDS. A point occurs when your VDS is becomes equal to VOV, this a value, VDS equals this value, the VOV, the VGS minus VT value, right? So it means at this point, what is happening? You can see channel at the drain is just pinched, right? It is reducing the depth, channel depth is reducing, but now it's pinched, right? So then, because it pinched, so because this is VOV and this is 0, not VDS, VOV minus VDS. This here we have 0 VDS because VOV is equal to VDS. So VOV minus VDS is 0 here. So 0 depth and VOV depth. So half is half VOV. So now your GDS is half VOV. Kn half VOV. So it means your formula is now changed again. You can put from this half Kn VOV and VDS. So this is only for previous region, and this previous region is called triode region, right? We have a band here, initially proportional and then having a band here. So this is called triode region. So triode region can be marked with the value of VDS less than VOV, right? Because VDS was small in millivolts, further increased, but before the point where the pinch off occurs, right? VDS equals VOV. VDS equals basically this is VOV, sorry. So VGS minus VT or VOV. So before that, VDS is less than VGS minus VT or VOV, right? So at this point, pinch off occur and your current saturates, right? And now your formula is this one, okay? So what if I increase VDS further than this point? This formula intakes or not? Yes, it intakes, right? So it means at this point, the pinch off point, you are having separated two regions, triode region and the saturation region. Triode region having formula already said to you, right? KnVOV minus half VDS, right? And in saturation, half KnVOV square or half KnVOV into VDS, because at this point VDS and VOV is the same, so VOV square, right? So now if remember this formula, this formula is valid only for this boundary value because your VDS is this one. Now if you increase your VDS, you cannot use this formula, you have to use this formula because VOV and VDS are different because you are increasing your VDS. But at this point, when the VDS equals VOV, you can use VOV square because VDS is equal to VOV. Okay, so this region is called saturation region where VDS greater than or equal to VGS minus VT. Okay, so previously in trans BJT, the region near to zero was saturation region and another one is called the active region. Here we have a triode region and the active counterpart is saturation region, and this is the important region. This is the important region in which we will design amplifiers, right? So current saturates means it becomes constant because the channel is pinched off and now current will no more increase even if you increase your VDS. But let me introduce you here, not much significantly increased, right? Remember the early effect. So it will affect but very small effect, so we can neglect it at this point at least, right? We will consider it later. Okay, so at this point only you can use this formula VOV square, otherwise come here, put VDS whatever it is and VOV is separate. Okay, VOV is VGS minus VT. Okay, so now we are at the stage to introduce the symbols of the MOSFET. What is this new thing? Enhancement type. Enhancement means you have no channel until you apply VGS greater than VT. Okay, so as you applied VGS greater than VT, channel is formed. As much you increase your VGS greater than VT, VOV increase. your channel is more enhancing, having more depth. So this transistor is called